Here we have a question where it's going to ask you to find the equation of the tangent plane to the graph of this massive equation here. And it's told us the point at AB11. So this is quite a big question, and there's one equation that you need to know. This is something that you'd probably look at university level, and it would be in your calculus exams, or maybe differential equations. I don't really know what many syllabuses are like. You're looking at quite a bit of differentiation here. You probably do it in second semester, first year, maybe first semester, first year. It wouldn't really be a second year topic. You should be doing this in first year. And basically, this is what you're going to have to do. You have to remember this one equation, and it's DFF x, whoops, messed up straight away, DFF d of x a b x minus a plus DFF dy a b multiplied by y minus b minus z minus f a b equals 0. Bit of a mammoth equation there. It's a bit weird. You're probably looking at it like, what are you talking about? But it will all make sense. You write this out a million times and eventually you'll remember it. I don't think you've given it in your exams, so just remember this equation. So anyway, let's break it down. So let's now get this problem, and let's now I don't like brackets. I'm not a fan of them. So let's just get rid of those brackets. We'll get x squared y plus xy minus x squared y squared. There you go. So that's my problem. Let's now differentiate this in terms of x. So my DFF dx. Now that literally just means you hold the y constant. So we get 2xy plus y, because if you're only differentiating x differentiates into 1. So you get y minus 2x y squared. So now here is my answer. But now they've given me the points a and b is 1, 1. So I substitute them in. So you get 2, 1, 1 plus 1 minus 2, 1, 1 squared. You see, so I've plugged all 1 and 1 into df of x dx, which is df of x dx ab. So because obviously that implies with ab being substituted back into the differential of df dx, which would that means be 2 plus 1 minus 2, which equals 1. So now I've got my df dx. Now let's do df dy. My df dy of this is x squared plus x minus, differentiating this would be 2yx squared. Again, instead of you are holding your x terms as constants, and you are only differentiating the y terms. As you can see, I've held all my x terms constant and only differentiated the y terms. Now let's plug in ab, which is 1, 1, and that would be 1 squared plus 1 minus 2, 1, 1 squared. So you'll get 1 plus 1 minus 2. So that would actually equal 0. So that's my answer for df dy. And now let's do FAB. So now FAB, that's when the function here has AB plugged into it. So you'll have 1 squared times 1 plus 1, 1 brackets 1 minus 1, 1, blah blah blah. Or plug it into this. So you'll get 1 plus 1 minus 1. So that means FAB. I crossed out the wrong thing there. It should have been, this shouldn't have been crossed out. This should be crossed out. 1 plus 1 is 2, minus 1 is 1, equals 1. So now here I've done a bunch of the groundwork. So I've done a lot of the groundwork here, and now we're going to now use this big mammoth equation. So as you can see here, we have dff dx ab multiplied by x minus a plus dff dy ab multiplied by y minus b minus brackets z minus FAB all equal to naught. That is my equation, my kind of template, let's call it a template, that I'm going to use my formula. And I'm now going to plug these everything that I've calculated here, I'm going to plug them into this. So I've got DFF dxAB, which is 1, multiplied by x minus, now x minus a is 1. It says here AB is 1, 1, like this. Plus df dy, which is 0, and y minus b, which is y minus 1. Minus z, brackets, remember the brackets with a minus, is, you must always remember the brackets, is minus z minus FAB, which is this, which is 1, equal to 0. That means x minus 1 plus 0, so this obviously gets cancelled out, let's say 0, minus z plus 1 equal to 0. So that means x minus z, so you've got minus 1 plus 1 is 0, so equal to 0. So now basically here, my equation would be x equals z. So this is the equation to the tangent plane. So as you can see, a quick summary, a bit of a run through as to what I've actually done. I've got the equation, I've differentiated it in terms of x, I've differentiated it in terms of y, I've then plugged in the point in which it's given me to give me two numbers. I've then also, the third thing I've done is taken AB and plugged it into f of xy. So now by plugging it into here, I've then also got my third value. I then have remembered this equation and I have plugged in each point and got x equals z. So this is the equation to the equation of the tangent plane to this graph.